Hi. In this video, we'll come up with a new problem, and in this question, we are again going to deal with properties of triangles and in continuation with the theory about the triangle geometry that we have seen in the last few videos. So let's get into the question. The question says that ABC is an isosceles triangle with AB equal to AC and I is the incenter. Now T1 is the circle centered at A with radius AB, and T2 is the circle centered at I with radius IB. Now we say there is another circle. Suppose T3 is the circle passing through I and B, and it will intersect the first two circles T1 and T2 at P and Q respectively. And these intersection points are obviously different from B. R is the intersection point of IP and BQ, and we have to prove that BR is perpendicular to CR. So we'd have to draw a figure here and try to understand what is going on. So let's draw an isosceles triangle first. Okay, I'll just draw it like this. This is my isosceles triangle. A is here, B is here, C is here. AB is equal to AC. So T1 was the circle centered at A with radius AB. So if you think about it, center is this for T1, radius is AB. So it will pass through AC, right? It will pass through C as well. That's what I mean. Because AB is equal to AC, right? So there is a big circle here. This circle is T1, right? The center of this circle is A. Now the in center of the triangle will be somewhere here. This is my I, which is the angle bisectors, the point of intersection of angle bisectors. And now IB is a radius. IB is a radius, and from here I make the circle 2, right? T2. So it's a circle with radius IB. So it will be like this and roughly like this. This is my circle 2, right? We don't care about the exact drawing of the circle here. We just know that the circle passes through B and center is I, and this is my circle 2, T2, right? Okay. Now what is circle 3? T3 is the circle passing through I and B. The circle passes through I and B and it intersects T1 and T2 at P and Q, right? So let me make a circle passing through I and B like this. Like this, right? Or slightly better figure. I will make it, I will intersect it here. This is the circle. This passes through I and B and intersects T1 and T2. So this must be my P, T1 at P. So this is my P and this is my Q, right? So this is my T3. T3 is a circle through I and B and passes through P and Q. You have to realize that P is the intersection of T3 and T1 and Q is the intersection of T3 and T2, right? So that is my figure. You should draw a more magnified version of this figure. That will make things much clearer. So what we will do here is we have to prove that BR is perpendicular to CR. Also, R is the intersection point of IP and BQ. So you have to join IP and we have to join BQ. So it is better if I do this thing on the next screen. So I will just draw a magnified figure here. Let's do it like this. This is my ABC here. A, B, C. And my in center would be here, I. My first circle passes through B and C. And the center is this. This is T1, right? The second circle passes through I, and the second circle is centered at I. So center is I. So the second circle looks like this. Okay, that is not correct. We'll draw a circle like this. This is my second circle roughly. The center of this circle is, this is my T2. The center of the circle is I, right? The third circle, T3, passes through I and B. So if I draw the figure like this is a better figure. It is clear that this is T3 and this intersects this at P and this at Q. And we have to find the intersection point of IP and BQ. So we can join BQ, this straight line, and IP, this straight line. And this becomes my R. And we have to prove that BR is perpendicular to CR. CR is this and BR is this. We have to prove that this angle is 90 degree, right? It's an isosceles triangle. I is the in center, and the circles T1 and T2 have centers at A and I. And the T3 circle passes through I and B, right? So first step is to join the line segments IB, IC. Let's join the line segment here, IC. Let's join PB, PB, PC, IB, IC, PB, PC, and IQ. We will join these line segments so that we have different triangles and quadrilaterals here. And we'll think about what to do now. Now we notice that Q lies on T3 and T2. Q lies on the intersection point of T3 and T2, right? And we know that IB is equal to IQ. Why do we know that IB is equal to IQ? Because IB was the radius of IB is radius of T2, and I was center, right? I was center of T2. Therefore, since Q lies on T2 also, then IQ is also a radius of the same T2 circle, right? So we know that IB is equal to IQ. That is guaranteed because they are radius of the same circle. Great. So because IB is equal to IQ, we know that angle IBQ is equal to angle IQB. In triangle IBQ, we have an isosceles triangle. IBQ is equal to IQB, these two angles. And we know that since IBPQ is cyclic, you can see that IBPQ all lie on the circle T3. Circle T3. Therefore, angle IQB is equal to angle IPB. Is equal to angle IPB. Why is IQB equal to IPB? Because they are subtended by the same arc IB of circle T3, right? So IQB is equal to IPB and IQB is also equal to IBQ. So this implies that angle IBQ is equal to angle IPB, right? Angle IBQ is equal to IPB, right? Okay. Now we can prove that triangle IBP is similar to triangle IRB. How do we show that? Triangle IBP is similar to IRB, right? So first of all, Let's draw the figure in a smaller sense, in a magnified way. Let's say I is here and B is here and P is here. So we know that this is joined like this. Let's not mark P here. We'll mark P here, P here, and Q here. We will join IBP, and PQ is like this, and PQ and IP will meet at R. Let's say R is here, right? I want to show that IBP is equal to IRB, right? So for that, I already have IBQ angle is equal to IPB angle. IBQ angle is equal to, first of all, notice that this angle is common to both, right? In triangle IRB, we have angle I here. And in triangle IBP also, we have angle I here, right? So is there any other common angle? Yes, I think there is. We can say we already know that angle IPB is equal to IBQ. This angle is equal to this angle, right? So let's say this angle is theta. So this angle is theta. So what is this angle? This angle must be 180 minus theta minus angle I, right? And in the triangle IPB, this angle is also 180 minus theta minus angle I. So we can say that IBP is equal to IRB, right? Angle IBP is equal to angle IRB by just checking all the three angles of the triangle. And we also know that angle BIP is equal to angle BIR. So by AA similarity, we get these two triangles are similar. And if the triangles are similar, we can say now that IB by IR should be equal to IP by PB by IB. You can check the similarity ratio yourself. This is happening because the triangles are similar by AA similarity, right? Now, we can say that in triangle ABC, AB was equal to AC. AB was equal to AC and I was in center. I was in center. Therefore, that implies that IB should be equal to IC. Why should IB be equal to IC? It's an isosceles triangle. So the line, the angle bisector here divides, the angle bisector AI basically divides the isosceles triangle into two halves, right? Two congruent triangles. Also, you can just say that the length of IB, the length of IB is R by sine B by 2 and length of IC is R by sine C by 2. And since AB is equal to AC, angle B is equal to angle C, so this is IB and this is IC. So IB is equal to IC. Therefore, in our ratio here, I can write this as IC by IR is equal to IP by IC, right? I have replaced IC with IB. Instead of IB, I have written IC both places, right? So now you can also show basically because of this that triangle ICP is similar to triangle IRC. Think of these two triangles, ICP and IRC, right? So anyway, you have this angle is common to both the triangles, and we have the ratio of the sides also coming, right? There is a ratio of the sides IC by IR is equal to IP by IC, right? And we have a common angle. So that means these two triangles are similar definitely, right? When you have one common angle and ratio of two sides is same, the triangles are similar, right? Okay. So now what we can say here is this implies the similarity basically implies that angle IRC must be equal to angle ICP. Once we have proved that the triangles are similar, you can say that all the angles are equal. So angle IRC must be equal to angle ICP, this angle, right? Great. Okay. Now what we get down to is the overall circle. So we can say that P lies on arc BC. P lies on arc BC arc on T1. Therefore, angle BPC should be equal to 180 degree minus half of angle A, right? Why? You can understand that easily if you just draw one circle, big circle like this, and this is my BC and this is my A, then angle BPC, P lies here, right? So angle BPC, actually the center of the circle was A. A was the center, right? This was the circle T1. Arc BPC will subtend some angle here at the center. So that means this arc should subtend us half of that angle here, right? So angle A, so whatever is this angle, double of that is A, right? So we can say that the arc subtends 360 minus A, the upper arc subtends 360 minus A here. So angle BPC should be 180 minus half A. We have to look at the upper arc here. The upper arc subtends angle 360 minus A at the center A. So therefore it should subtend an angle half of that, 180 minus A by 2 here, which is BPC, right? You should draw a bigger figure and you will get it. So just look at the arc here. Which arc? The arc from here, this arc, right? Actually, this is circle T2. So we have to look at the circle T1's arc. Circle T1's arc is very big. It is above and beyond here. So look at the arc B like this till here, what it subtends here, the angle here. This angle is 360 minus A. So since this arc subtends 360 minus A at its center, it should subtend half of that, which is 180 minus A by 2 at P, right? P lies on T1, right? So now angle BRC that we want to find, angle BRC. Angle BRC is equal to angle IRB. What is BRC? BRC is same as IRB plus IRC, right? IRB plus IRC. And we already know that angle IRB is equal to IBP. So this is angle IBP plus angle IRC is equal to angle ICP. So this is angle ICP and IBP, right? Now look at the quadrilateral IBPC. IBPC quadrilateral. In that quadrilateral, IBP and ICP are two angles of the quadrilateral. So the addition of those two should be equal to 360 degree minus angle BIC minus angle BPC, right? correct? Just by looking at the quadrilaterals, we can figure out that quadrilateral IBPC, we can figure out that angle BRC is IRB plus IRC. We have already shown that IRB is IBP and IRC is ICP. And these are two angles of the quadrilateral. So the addition of the two angles should be 360 minus BIC minus BPC. Now what is BIC? By basic properties of in-center, angle BIC is equal to 90 degree plus angle A by 2. And we have just now shown that angle BPC is 180 degree minus angle A by 2, right? So this is minus 180 degree minus angle A by 2. So if you calculate this now, it is 270 minus 180, which is 90 minus A by 2 plus A by 2. So this is 90 degree. So we are able to show that angle BRC is equal to 90 degree. Obviously, it has taken us some steps. We are now getting BR perpendicular to CR. The steps involved are realizing basically that BIPQ is cyclic quadrilateral. From there, we were able to conclude that triangle IBP was similar to triangle IRB, and we got a similarity relation there. And because AB was equal to AC, we got IB equal to IC. And because IB was equal to IC, we got IC by IR is IP by IC. And then we concluded that one angle was common and ratio of two sides were same. Therefore, triangle ICP is similar to triangle IRC. And from there, we get IRC is equal to ICP. And then we look at the actual angle that we have to figure out, the angle BRC, which is BRI plus CRI, which is equal to IBP plus ICP, and we get it. So hopefully you've understood the problem. The problem is difficult because the figure is difficult to get. Once you understand the figure, you have so many properties of circles and triangles that are applicable here. Let's look at another question. This one is in triangle ABC, let D be the point of tangency of the incircle I and BC. The line DI intersects AC at X, and let XY be the tangent line to the incircle. It is given that XY does not coincide with AC and Y lies on AB. Now let Z be the intersection point of YI and BC. We have to show that AB is equal to BZ. Okay. So again, first thing is to draw the figure properly. We have a triangle ABC. A, B, C. And the in center is I. So let's draw angle bisectors. This is my in center. And the D is the point of tangency of the in circle with BC. So we have to drop a perpendicular on BC. This will be my D. And this will be my in circle roughly. I will draw the in circle later. Line DI intersects AC at X. So we have to extend this like this. And this becomes my X, right? And let XY be a tangent to the in circle. Now I have to draw the in circle first before I can draw my tangent. So my in circle will be like this. So this is the wrong figure. In circle will pass through these and touch it here. This is my rough in circle. Now xy is the point of xy be a tangent line to the in circle. So from here x, I am drawing a tangent with y lying on AB. So this is my y. So this is my tangent line. xy is a tangent, right? Y lies on AB. Okay, so y is basically the point of tangency of the circle and the AB line, right? Okay, now z is the intersection point of yi and BC. So we extend yi and this is my z. Correct. Now we have to show that AB is equal to BZ. The side AB is equal to BZ. Okay, fine. This is my figure. So if you think about it now, you can look at the in circle and you can notice that there is a triangle AXY. If you just draw the triangle AXY like this, think about it. It has extended sides like this, A, X, Y. And the in circle is basically touching the sides XY and AY and this side, right? I feel like there is something wrong with the figure right now. There is something wrong with the figure. You cannot have two tangent lines here. So, like, you cannot have two different tangent lines. The y point, xy is a tangent line, right? But y lies on this. Okay, so I have made a mistake in the figure a little bit. I will just redraw the figure. So I'll draw a slightly bigger triangle now. Slightly bigger triangle. This is A, B, C. The in circle, the in center would be angle bisector. So let's bisect this angle. Let's bisect this angle. This is my I. And let's drop a perpendicular here. This is my D. And let's extend it here. This is my X. And let's draw the in circle. So perpendicular to this side would be like this. The in circle would be like this. Something like this. Obviously, it's not accurate, but this is the point where the in circle touches the side AB. Now, from X, I have to draw tangent to this circle. So I will draw a tangent like this. The point of tangency is here, but y is this one, this point, right? Y does not coincide with this. This is some other point where the side AB was tangent to the incircle, because you cannot have two different slopes of the tangent here, right? So y should be here, and this is the point of tangency of xy line with I. Now you can see clearly in the figure triangle AXY. Triangle AXY is like this, and the incircle is basically touching all the extended sides, right? This is my X and Y and A. The incircle touches these extended sides here, right? So I was the center of the circle. I becomes the X center for triangle AXY, right? So we can say that in center I is the AX center of triangle AXY. And therefore, by the properties of X centers, we know that if I join YI, YI was intersecting with BC somewhere here, Z. So if I join YI and XI, I know angle XIY is equal to 90 degree minus half angle A. This is a property of X center that we have already discussed in the theory section, right? Great. Now we look at angle IZB. IZB. Angle IZB is equal to 90 degree minus angle DIZ. DIZ. Because obviously this is a right angle triangle. So this angle is equal to 90 degree minus this angle. And angle DIZ is equal to angle XIY because of vertically opposite angles. So this is 90 degree minus angle XIY. And therefore XIY is 90 degree minus half A. So this becomes 90 degree minus 90 degree minus half angle A. So this is angle A by 2. Angle IZB is coming out to be angle A by 2, right? So this angle is A by 2. Great. Now IZB is equal to basically IAB, right? Why? Because when you make the incenter, if I join I and A, this angle is A by 2, right? So we have angle IZB is equal to angle IAB. We also have angle IBZ. IBZ is equal to angle IBA. IBA. Because BI was the bisector of angle B, right? And we have IB is equal to IB. So in triangles ABI, we can say that triangle ABI is simply congruent to triangle IBZ, right? This is directly SAS congruency. SAS congruency, we are getting ABI is congruent to IBZ, therefore AB is equal to BZ. This is a much simpler question. The only thing you have to realize is draw the figure properly and realize that angle XIY is equal to 90 minus half A. Once you get that, because it's the AX center for triangle AXY, you can just say that this angle is 90 minus half A, so this angle is 90 minus half A, so this angle is A by 2. This angle is A by 2 means this angle is A by 2, and this is a common side, and this angle is B by 2, and this angle is E by 2. So triangle ABI and triangle IBZ are SAS congruent, and therefore AB is equal to BZ, right? So I hope you learned something from this one. Let's look at a final problem, and then we'll be done. This is question number 3. We have Let O be the circumcenter of triangle ABC. Let K be the intersection of CO and the altitude above BC. P and M are the midpoints of AK and AC respectively. The lines PO and BO intersect at Y, and the circumcircle of triangle BCM intersects AB at X, which is not equal to B. We have to prove that B, O, X, and Y are concyclic points. Okay, so let's draw the figure roughly. We have a triangle ABC. A, B, C. We have a triangle ABC. K is the intersection point. O is the circumcenter of this triangle. K is intersection point of CO and the altitude above BC. So the altitude above BC basically means the altitude from A to BC. This is an altitude from A. The perpendicular bisectors will intersect somewhere here. So this is my O, which is the circumcenter. So I will join CO. CO and altitude intersect at K, right? So this becomes my point K. And P and M are midpoints of AK and AC. So M is somewhere here. M is the midpoint here. We have drawn perpendicular bisector from this, right? And K midpoint is P. P is here. This is the midpoint of AK, right? Okay. Lines PO. Okay, so line PO and BC. So we join P and O, and BC will intersect here. And this point is Y. The line PO and BC intersect at Y. And the circumcircle of BCM intersects AB at X. So we have a rough triangle here, B to M, BCM circumcircle. So we can draw a rough figure. It will be a circle like this. This is obviously very rough. We are just going to say this intersects here at X, right? We have to prove that B, O, X, and Y are concyclic, right? This circle is the circumcircle of triangle BCM. So keep that in mind. In order to prove that BOXY are concyclic, we need to show that angle ABY, angle ABY plus angle XOY should be equal to 180, right? If we can show this, that this angle ABY or XBY plus XOY is 180, that's a cyclic quadrilateral. So we have to show that angle ABY is equal to 180 minus angle XOY, and 180 minus angle XOY is equal to, if you see, it is equal to angle XOP, right? Because PY is a straight line and XOY is like this. XOY, that angle will be 180 minus XOP, right? So I have to show that ABY is equal to XOP, this angle. Okay. This and this angle are matching, right? So in order to show that, let's start by looking at triangle XPA. We'll first join X and P. Triangle XPA and triangle XOM. XPA and XOM. Okay, so XOM will be like this, right? In these two triangles, we have angle ABC Okay, before we think about this, we should realize that BXMC are cyclic, are concyclic points. BXMC is concyclic, so we know that angle ABC plus angle XMC is equal to 180 degree, right? So angle ABC is equal to 180 degree minus XMC, right? Because this sum up to 180 degree, ABC angle should be equal to 180 minus XMC, which is equal to angle XMA. XMA is this angle, right? Okay. So we are getting ABC is equal to XMA, and we have angle XMO. Angle XMO is equal to 90 degree minus angle XMA. Because the angle here, this angle is 90, so angle XMO is 90 degree minus XMA, which is basically now 90 degree minus angle ABC. Angle XMO is 90 degree minus ABC, right? And 90 degree minus ABC is basically equal to angle XAK, because 90 degree, this is 90 degree minus ABC, right? This angle is 90 minus ABC, and that is equal to XAK, right? We are getting XMO is equal to XAK. XMO is equal to XAK, correct. Okay, we have this much information right now. Now, we look at, since B, X, MC are cyclic, we have triangle AXM, triangle AXM is similar to triangle ACB. This is true. This is obviously true because AXM is this. One angle is common between AXM and ABC. Angle A is obviously common. And we have just now shown that angle XMA was equal to angle ABC. So we already know that angle XAM is equal to angle BAC, and we have just now shown that angle XMA is equal to angle ABC here. So by AA similarity, we know that these two triangles are similar. So therefore, AX by XM should be equal to AC by BC, right? Great. Now, O is the circumcenter of triangle ABC. Therefore, angle OCA, OCA, that angle is equal to 90 degree minus angle ABC. Why? Because this whole angle would be 2B. So this angle would be angle B. And this is 90. So this is 90 minus B, right? That is correct. And angle AKC, AKC is equal to 180 degree minus angle A. Angle A is basically XAM, right? Angle AKC we can draw a perpendicular from here, right? And we can see that these lines are parallel because O is the circumcenter, this is parallel. So we can say that angle AKC is this angle that is equal to 180 minus this angle, right? Because the line AK is parallel to this line, angle AKC is equal to 180 minus this angle. This angle is equal to this angle by vertically opposite. And this angle is angle A because it is the angle made by OC and this perpendicular. This is angle A, so this is angle A, so this is 180 minus A. I hope you get it. Basically, I have dropped a perpendicular from here and these two lines are parallel. So this plus this should sum up to 180 and this is vertically opposite of this and this angle is angle A. Why is it angle A? Because when I join OP and OC, the whole angle is 2 angle A. And this is congruent, so this is angle A. So we get angle AKC is equal to 180 minus A, right? So now, if you do, let's do it here. If you do the law of sines in triangle AKC, and triangle ABC. Sine rule basically in triangle AKC and ABC. We can say AC by sine of angle AKC. AC by sine of AKC should be equal to AK by sine of angle KCA, which is 90 minus B, right? So this becomes AC by, this is AKC is 180 minus A, so this is AC by sine A is equal to AK by cos B, right? So now we are getting from here that AK is equal to AC cos B by sine A, right? And we also know that OM distance is equal to OC cos, this is 90 minus B, so OC sine 90 minus B. So that is OC cos B. OM is equal to OC cos B, right? So therefore, AK by OM will become equal to AC cos B by sine A divided by OC cos B, right? So cos B gets cancelled and we have AK by OM is equal to AC by OC sine A, right? Okay. Now we know that P is the midpoint of AK. P is midpoint of AK. So therefore, AK is equal to twice of AP, right? So we can write, instead of AK here, we can write AP by OM. So I will do that here. We can write 2AP. So AP by OM will come out to be AC by 2 OC sine A. The 2 has been brought down from here to here, right? 2 OC sine A. Now 2 OC sine A is basically 2R sine A, right? OC is the radius of the circumcircle. So 2R sine A is what? If this angle is my A and 2R, this is R. So R sine A would be this length, right? So 2R sine A would be this length, would be BC, right? So we are getting AP by OM is equal to AC by BC, right? Great. AC by BC is equal to AP by OM, we have gotten. And since we had similar triangles XPA and XOM, we already have AX by XM. We already had AX. Actually, we have already shown here this. AX by XM is AC by BC, right? So now what are we getting? AC by BC is AP by OM. So we are now getting that AX by XM is equal to AP by OM, right? AX by XM is equal to AP by OM, right? Now we can say that in triangle XPA and XOM, XPA and XOM, we can say that these triangles are now similar, right? Because the ratio of the sides is coming same. AP by OM is equal to AX by XM, right? And one angle is also matching. This angle is matching this angle, right? So we are getting the triangle XPA is similar to triangle XOM. And similarly, we can also show that triangle XOP is similar to triangle XMA. Triangles XPA and XOM are coming similar because we got this ratio and one of the angles are matching anyway in those triangles. And now, since they are similar triangles, therefore angle XOP is equal to XMA, which is equal to angle ABC, right? We are getting angle XOP is equal to angle XMA, which is equal to angle ABC. So XOP is equal to ABC is coming, right? XOP is equal to ABC. Once we have XOP is equal to ABC, ABC is clearly equal to angle ABY. And that is what we needed to prove. If you remember in the beginning, I said that we need to prove angle ABY is equal to angle XOP. That was the initial condition for the BOXY points to be concyclic. So you have to go back to the previous screen and you will be able to see this was written. XOP should be equal to ABY. And we are getting there by similarity of triangles XPA and XOM. And for that similarity, we did a lot of stuff. So you should rework through the question yourself, pause the video, go back and see what are the steps involved. And hopefully you will be able to understand. The question is a little complicated, this one, but this is typical of Olympiad problems. There are many things that you'll have to get. The concepts are basically elementary, but there are so many connections that you have to make in order to come to the right conclusion, right? So hopefully you learned something from this video. And that concludes our section on triangle geometry. We have another geometry section after this, which is some more theorems on geometry plane geometry that is required for Olympiads. We'll do a few problems and learn some more theory. And that will conclude the geometry part for now. We'll come back to geometry later. So that's it for this video. You hope you have learned something from it. I'll see you next time.